Hello everyone, and welcome back to the channel. In this video, we are going to look at the stack and how it is used in modern computers. The stack is a vital part of a computer's memory management system. It is a dedicated area of memory. It is not a separate physical location, but a logical division within the computer's memory space. A stack is a linear data structure that follows the last in first out principle. This means that the last element added to the stack is the first one to be removed. Think of it like a stack of plates. The last plate you put on the stack is the first one you take off. Before we look at how a stack manages function calls, let us first understand the essential components of a stack. The stack pointer is a register often stored in the ESP register on x86 32-bit mode, or RSP register on 64-bit mode. It points to the current top of the stack. It tracks where the next push or pop operation will occur. If memory addresses 100 to 1000 are allocated for the stack, it will start at memory address 1000 and not 100. As data is added to the stack grows downwards from address 1000 towards address 100. The stack pointer is crucial for maintaining the current state of the stack during function calls and returns. A stack frame is a section of the stack that is dedicated to a single function call. A program usually has multiple functions. Each function will have a dedicated stack frame. They are like a little box for each function in the memory. It includes all the information needed for the function to execute and then return the control to the calling function. A stack frame typically holds 5 elements. Function parameters are the arguments passed to the function. Return address is the memory address to which the program should return after the function completes. An old frame pointer is a fixed pointer that references the calling function's stack frame. Local variables are any variables that are defined within the function itself. Since a typical program contains multiple functions, it's essential to distinguish between the different stack frames. This task is assigned to the frame pointer. The frame pointer, often stored in the EBP register on x86 32-bit mode or RBP register on 64-bit mode, is a pointer that remains fixed at the base of the current stack frame. It provides a stable reference point for accessing function parameters and local variables within that frame. Using a frame pointer is helpful because while the stack pointer changes as the stack grows and shrinks, the frame pointer stays constant within a function call. There are 2 kinds of frame pointers which can be a bit confusing. So let us differentiate between the 2. The first frame pointer is the old frame pointer. Every function has a stack frame, and each stack frame always has an old frame pointer. The old frame pointer allows the function to return to the calling function once it has finished executing. In C, the program starts executing at the function main. Therefore, main does not have any function calling it. But still, an old frame pointer is pushed onto main stack frame. Since no function is calling main, the value for the old frame pointer is either 0 or some placeholder value. The location of the old frame pointer is called the base of the stack frame. Even though the location of the old frame pointer is called the base of the stack, there is one element below the old frame pointer, the return address. The return address is the address of the instruction that should be executed once the current function has been completed. Although the return address is technically pushed onto the stack before the old frame pointer, it's often considered part of the calling mechanism rather than the base structure of the frame itself. The frame pointer, being specific to the current function, serves as the primary base reference. The second pointer, called the current frame pointer, points to this location of the old frame pointer. The current frame pointer's role is to keep track of the active stack frame. The current frame pointer is stored in a register and is not an element on the stack, whereas the old frame pointer is an element of the stack. When main calls another function, first, a new stack frame is created for that function. Then, the value of the current pointer is pushed onto the new function's stack frame as the old frame pointer. Next, the current frame pointer is updated by pointing it to the location of the old frame pointer. Now, the current frame pointer points to the base of the called function. This process is repeated for every function call. Now let us look at how a stack process function calls. This code written in C has a main function and an add function that is called by main. When main begins, the stack will be empty or may contain some runtime environment data if set up by the OS. Since main is a function, a new stack frame will be created. Once the stack frame for main is created, the return address will be pushed to the stack. Since main is the entry point for the program, a dummy return address is pushed onto the stack, pointing to the program exit or cleanup function. After the return is pushed onto the stack, the old frame pointer is pushed to the stack. Since main has no caller, the old frame pointer is often set to 0 or some placeholder value. After the old frame pointer is pushed onto the stack, another pointer points to this location. This pointer is called the current frame pointer. The current frame pointer is stored on a register and is not an element on the stack. The current frame pointer is used to process the main stack frame by providing a point of reference to access elements inside the main stack frame. When main calls the add function, a new stack frame is created for add on top of main's frame. First, the return address is pushed onto the stack. The return address for add is the instruction that the program needs to execute once the function add has finished executing. In this case, the return address is the next instruction in main, right after the call to add the printf statement. Next, the current frame pointer from the register is pushed onto the stack as the old frame pointer. This allows add to restore main stack frame when add finishes. After the old frame pointer is pushed onto the stack, the current frame pointer is updated to point to the location of the old frame pointer on the stack. After the new frame pointer is set, the parameters x equals 5 and y equals 10, passed as arguments a and b, are pushed onto the stack. Next, add calculates the sum of a and b and stores the result in sum. After the last line of the function add has finished executing, it then prepares to return the result sum to main. Often, the result sum is passed back to main via a register like EAX in x86. To return the control back to main from the add function, the stack pointer is adjusted to point to the current frame pointer. Now the stack pointer points to the old frame pointer on the stack. Next, the old frame pointer is popped and is assigned as the new current frame pointer. This means that main is now the active stack frame. After that, the top of the stack, which is the return address, is popped. The CPU jumps to the return address for main, allowing main to continue from where it left off. Finally, main completes and returns using its own dummy return address, which triggers the program exit routine. The runtime environment cleans up main's stack frame, freeing all allocated memory. The stack is now back to its pre-programmed state. Now let us look at how the stack plays a vital role in evaluating expressions. Let us take this mathematical expression as an example. This format of writing an expression is called an infix notation. While this is how we usually write expressions, computers use another type of notation called the postfix notation. Before evaluating the expression, we need to convert the infix expression to postfix. First, we need an empty stack and a variable to hold the output. Then we must follow a set of rules to convert the expression. Let us see how this rule works with our example. First, we need to scan the expression from left to right. The first item is a left parenthesis. Whenever we see a left parenthesis, we have to push it on the stack. The next item is a number or an operand. Whenever we see an operand, we must add it to the output. Next, we have the plus operator. Operators must be pushed on the stack if the stack is empty or the top element is a parenthesis. Then, we have the number 4, which is an operand. So, add it to the output. Next, we have a right parenthesis. When we see a right parenthesis, we have to pop the elements of the stack till we see the left parenthesis while discarding the 2 parentheses. The popped elements are added to the output. The next item is a multiplication operator. Since the stack is empty, we push it to the stack. The next item, 2, is an operand, so we add it to the output. The next item is the minus operator. If the incoming operator is left associative, like plus, minus, multiply, and divide, and has lower or equal precedence to the element on the top of the stack, pop operators from the stack to the output until either the stack is empty, a left parenthesis is encountered, or an operator with the lower precedence is at the top of the stack. Then, push the incoming operator to the stack. If the incoming operator is right associative, like the exponentiation operator, and has lower or equal precedence to the element on the top of the stack, we push the incoming operator to the stack. Here, we have minus, a left associative operator, which has lower precedence than the operator on the top of the stack. So we pop the stack, which has only one item, and add it to the output. Then we push the minus operator to the stack. The next item is 5, so it is added to the output. Then we have a division operator. If the incoming operator has higher precedence than the one on the top of the stack, we must push the operator to the stack. So we push the division operator to the stack. The next item is a left parenthesis, so we push it to the stack as before. Next, operand 2 is added to the output as before. The next item is an exponentiation operator. The top of the stack is a left parenthesis, which is not an operand. In this case, we push the operator onto the stack without any comparison. The next item is 3, so we add it to the output. The last item is a right parenthesis. Pop operators from the stack to the output until a left parenthesis is reached and discard the left and right parenthesis. When we have finished scanning the expression and the stack still holds some elements, pop all the elements of the stack to the output. Now, the resulting output is in postfix notation. To evaluate a postfix expression, we use a stack to store operands temporarily. When we encounter an operand, we push it onto the stack. When we read an operator, we pop the required number of operands from the stack, apply the operator, and then push the result back onto the stack. Now let's evaluate the expression. First, we initialize the stack and then read the expression from left to right. The first item is 3, so we push it to the stack. The next item is 4, so we push it to the stack. The next item is the plus operator. So we pop 2 items from the stack and add them. The second number to be popped is taken as the first digit. After addition, we push the result back to the stack. The next item is 2, so we push it to the stack. When the multiplication operator is read, we pop 2 elements from the stack, multiply them, and push the result back to the stack. The next 3 items are all numbers, so we push them into the stack. The next operator is the exponentiation operator. So we pop 2 and 3, calculate 2 raised to the power 3, and push the result back to the stack. Next, we have the division operator. So we pop 2 elements, 8 and 5. Calculate 5 divided by 8 and push the result to the stack. The final item is the minus operator. So we pop 2 elements from the stack, calculate 14 minus 0.625, and push the result to the stack. At the end of the evaluation, the only item left in the stack is the result of the expression. Thank you for watching the video. I hope you learned something today. Have a beautiful day and see you in the next video.